So last section we're going to take a look at this week is the second half of 6.2. And just a reminder for anyone watching the video for the test. So if you are in period 2-3, then we will be starting the test on Tuesday, that's the 23rd, and we'll be finishing it on the 24th because we have a half day and our class does meet for half a period. If you are watching in period 5-6, then we do not meet, we do meet on Wednesday, so same exact thing. We will start the test on the 23rd and we will finish on the 24th. If you're watching in 7-8, then we do not meet on Wednesday, so we will do the whole test tomorrow. So we won't have quite as much review in class, but I am after school today, so if anybody does feel like they need more review or they want to go over anything, I will be here after school. Okay, so last time we left off with unit circle trig, and what did we say that the whole goal of unit circle trig is, or what do you have to be able to find to do anything with unit circle trig? You have to be able to find what? Yeah, you have to be able to find a coordinate. Okay, if you can't figure out the coordinate, then we can't do unit circle trig. We also only use unit circle trig for certain angles. Does anybody remember what I said? We always do angles that are multiples of what or what? And there's some overlap here too. John?
30 or 45.
Multiples of 30 or 45. Okay, and obviously like 90 is a multiple of both. Okay, but 30s and 45s are what we're going to use unit circle trig for. And that's what we're going to start by looking at today. So we're going to look at how do we find the 6 trig functions for angles that are 30, 60, and 45, and equivalently in radians. And how do we find the trig functions of multiples of those angles? Okay, so that's the first thing we'll take a look at. And then the working with trig identities, we're probably going to hold off on that. It's something they kind of squeeze in at the end of this section, but we're going to talk a lot more about trig identities when we get into material later on. So if we skip that right now, it's not really a huge deal. All right, so let's think about the angles that we already know coordinates for. We've got the 0, 90, 180, and 270. 0, and the coordinate for that is 1, 0. How about the coordinate for 90? What's that one? Sophie? 0, 1. Okay, how about 180? Coordinate for that one? Abel?
-1, 0.
-1, 0. And how about 270? Yeah, Matt?
0, -1.
0, -1. Okay, those are the quadrantal angles. They all have a 0 and a 1 in the coordinate. What we're going to look at first is the 45, the 30, and the 60. And you'll notice those 3 points are not spaced equally in the quadrant. There's a little bit of a gap between the black dot for 90 and the last red dot, and then between the dot for 0 and the first red dot. And that would be where the 15s would go. If we were going to do 15 and 75, those would go in right there. Then we would have every angle that's a multiple of 15. You can do the 15s. It's a little bit tricky because you need what's called a trig identity to do it. But we'll talk more about that later on. Okay? So let's start with the 45. So what I've done is I've drawn 45-degree angle and tried to make it look somewhat accurate. It's supposed to look like a ray that has a slope of 1 because we've gone over and up the same amount. Okay, that's a 45. So this would be 0, this would be 90, and it's halfway between. So, goal is to figure out the coordinates for 45 degrees. So to do that, we're going to make a shape inside that circle. Any guess what kind of shape we're going to make? Yes?
A triangle?
We're going to make a triangle. How do you think I'm going to make a triangle that's going to help me to get the coordinate from 45 degrees? John?
You go straight down from like 45 right there.
Yep. I'm going to go straight down, make a triangle. Now, the distance that you move from the origin to the right, what is that distance called in a coordinate? Yeah, that's called your x. So in other words, x here is the length of the bottom side of that triangle. How about the distance that you move from there up? What do you call that distance? That's your y. And that, in this case, is the height. So our goal is to figure out the base of the triangle and the height of the triangle. Now there's one side we already know. John?
It's the hypotenuse, right? We know that that has a length of 1.
We know the hypotenuse in that triangle has a length of 1 because it's the radius of that circle, which is a unit circle. Okay, so we know that's a 1. Unfortunately, 1 is the diagonal length from the origin to the coordinate. We need the horizontal and the vertical. So if we look at that triangle, that is a special kind of triangle. It's a right triangle. But does anybody have another term that we could use to describe it, besides being a right triangle? Yeah.
Is it a 2, 3, 5?
I don't think you couldn't have a triangle with sides of 2, 3, and 5. Because in a triangle, any two sides added together have to be bigger than the third. If they're not, then they don't.
Not to call it 2, 3, 5 ones.
I know what you're thinking of,
Yeah.
but no, it's not that. Yep.
Isosceles?
It is. This is isosceles. Right? It's isosceles because let's think about these angles. That angle is a 45. How do I know that? Because I have to tilt the hypotenuse at a 45-degree angle to hit the 45-degree mark on the circle. What do all the angles in a triangle have to add up to? Yeah. 180. Well, if you've already used up 90 and 45, that's 135. What does that leave for this top angle? Yeah, that has to be a 45. In a right triangle, if you have two angles that are the same, well, they both have to be 45s, because they all have to add up to 180. If they're both the same, that's isosceles. So what does that mean about x and y? Tim?
We can find them.
We can find them. And when we do find them, how will x and y compare to each other? Caleb?
They'll be equal.
They're going to be equal. So when I go to find them, I don't have to use two different variables. That's just going to complicate my formula. I can pick the same variable and use it for both because they really are the same length. Now I have a right triangle and I know one of the sides. How can you find other sides in a right triangle? There's a theorem you can use. Nick?
Angle, side angle. I figured out how to do that, but that's what it's called. The side angle side and the angle side angle.
So a lot of times we use those to prove congruence between two triangles, like side, 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 or side, side angle, or, well, side, side angle actually isn't one, but side angle side is one. But there's a different theorem I'm thinking of to find the length of a side in a right triangle, as long as you know the other ones. Yep?
Is it Pythagorean Theorem?
Yeah, we're going to use the Pythagorean Theorem. So let's set that up. And remember, we can use the same variable for the legs. We don't have to use two different variables. That will just make it look like the sides are different lengths, and they're not. Okay, so let's use x as the variable for my leg. So I'm going to have x squared plus x squared, because remember they're both the same, equals, and what's going to go on the other side? Tim?
1.
1. 1 what?
1 squared.
Yeah,
Which is
1
1.
squared. All right. Sophie, what's x squared plus x squared?
2x squared.
Good, 2x squared. Do not change that to x to the 4th. That's multiplying. So that was perfect. 2x squared equals 1. Now let's get x by itself. And there's the answer for the length of the sides. All right. Maddie, what will be my next step?
Divide by 2.
Divide by 2. So I get x squared equals a half. And Lindsay, my last step to get x alone.
Take the square root.
Take the square root. And when you take the square root of a fraction, just do the top and the bottom separate. So x equals square root of 1 over square root of 2. Annalise, what's the square root of 1?
1.
And square root of 2, we can't really do anything with that, but we also can't leave the answer like that. How do we fix having the square root in the bottom? Okay, at this point, we know the length of x. It's 1 over the square root of 2. We're just writing it properly now. Okay, we're going to rationalize the denominator. Yep.
Multiply top and bottom by square root of 2.
Exactly. Multiply top and bottom by square root of 2. And what will that give me in the top? Yeah.
Square root of 2.
Square root of 2 over 2. So, Tim, what's the length of the bottom side of this triangle?
Square root 2 over 2.
And how about the height of that triangle?
Same thing, square root 2 over 2.
Same thing, because it's isosceles. So we know how far we have to go over. We know how far we have to go up. Nick, can you just put that together for me and give me the coordinate for 45 degrees?
No.
So everything you need is right up there. You don't need anything back in your notes.
Square root of 2 and square root of 2 for x and y.
Can you just say it again?
Square root of 2 over 2.
Yep.
Square root of 2 over 2.
Square root of 2 over 2. Square root of 2 over 2. So that's the coordinate for 45 degrees all of the time on the unit circle. That never changes. If we want to do a circle that's not a unit circle, we can modify that a little bit and kind of figure out coordinates, but we're gonna stick with unit circle for most of what we do. Yes. Yes, Mr. Gabb.
Can you do 135 as an angle?
So we are going to talk about how to do multiples of those angles as well. Does anyone have a guess what that would be if we do 135? Because if you can do 45 in the first quadrant, you can do a 45 in any quadrant. How does that triangle in blue compare to the original triangle we had? Think about it as like from a geometry point of view. Yeah.
The x just inverse.
So what would the coordinate for 135 be?
Yeah, negative square root of 2 over
Comma?
2. Comma square root of 2 over 2.
Yeah. So anytime we do a 45-degree angle on the unit circle, the two numbers we always use are root 2 over 2 and root 2 over 2. We just have to decide if they're both positive, both negative, or one of each. Now the 45, that's the easier one. Okay, because both the x and the y value are the root 2 over 2. When we look at 30 and 60, we just have to be a little bit more careful. Okay, so we'll look at those next. All right, so, okay, we already went through that. All right, let's look at the 30, 60, 90. Okay. This one, you have to be a little bit more clever to figure out the coordinate. So let's start with the 30. Okay, so first of all, what would the angle right near the origin be? That's my, what, Mabel?
30.
Yeah, that's my 30. And what about the angle up at the top? That's 60. So what kind of triangle are we working with this time? Besides being a right triangle. What do we call this one? John?
Scaling.
Yeah, it is scaling. What does that mean? Yeah, Julie?
The two sides are the same.
Yeah, all the sides are different. Okay, so that means whatever we find for the x and the y, they are not going to be the same. But we do know one side already. What's the side that we know? John? Yeah, it is the hypotenuse. And Caleb, how long is it?
1 unit.
It's 1 unit. Now, if you tried to use Pythagorean Theorem on that right away, what would be the problem?
You'd have 2 variables.
You'd have 2 variables. You'd have x squared plus y squared equals 1. Well, if we're trying to solve for the sides, we can only have 1 variable in the formula. So that means you can use Pythagorean Theorem, but you have to find one of those variables a different way first. Okay, any thoughts what we can do? And there are things, if you had them memorized already, you would know the answer, because there's a relationship between the sides in a 30, 60, 90. But let's pretend like we don't remember that. And maybe for a lot, we don't even have to pretend. We probably don't. So, yeah.
Since the angle measures are like, since 30 is half of 60, is the length of 30 half of 60 and then 60 would be equal to 2x squared?
No. No. It's a good thought. But that's thinking linearly. And when we start looking at trig functions and when we graph them, they don't look like lines. So we can't really think along that line. Yeah.
Wasn't there some sort of like 30, 60, 90 thing where there's like square root 2 and stuff?
So there is going to be, square root of 2 comes up, but that one already came up in the 45, the square root of 2. So we're not going to see square root of 2 again in this one, at least on a unit circle.
Oh.
Let's just take that and go like that.
Sort of.
Give you one more hint. Yeah. John?
Wait, twice that would be like a square.
Okay, so
Well,
what are we thinking? What do you want me to do with it, what I got on the board?
Make a rectangle?
Okay, so we're kind of thinking along the right idea. I could try to make a rectangle, which means I would have to flip it twice, I think, like that. And there you go. There's my rectangle. Now what?
Find the area of the rectangle.
Because I have no idea what to do now. Find the area of the rectangle.
Or, well, the area would help you, but like the side lengths would.
Yeah, we need the side lengths. Do we have enough information to find the area of that rectangle? Because area is length times width. We don't know the length or the width. So I'm not sure we can find the area. But let's go back to that. Any other thoughts what I can do besides what we just did? Yep.
Can you put it on the bottom and make like an isosceles triangle?
So we could put it on the bottom. Boy, I really did not draw that straight. But that's okay. I'm going to fix it so it doesn't look as bad. Alright. bottom side is now nice and straight. Let's put that together and make a copy of that one. And let's flip it again like I had it. All right. So now when I put those together, let's think about what kind of triangle I have now. What's that angle right there?
60.
60. That angle?
60.
And what about that angle? What kind of triangle is that? Equilateral. Okay. All right, so what else do I know?
All the sides are 1.
All the sides are 1. Right? This side's 1, this side's 1, and I'll make them like this so they look like 1s. And that side is 1. Okay. What else? John?
When you, if you get half of the basis length, that's the length of y.
So explain to me, what's this length?
That's 1. And then half of that is y. Of course, it should be right.
Why would half of it be y?
All the sides are 1, and it's an equilateral triangle.
But how come you can take half of this number to get that? Why not take a third of it?
Because it's like bisected by.
Yeah, the key is these two sides are congruent, right? We know they're congruent because I made a mirror image of that triangle. So if the length of them in total is 1 and they're congruent, each one of them would have to be 1/2. All right? So now I know that that right-hand side is a half. I can move all this other stuff away and just look at what I have left. So now all I have to do is find the length of the bottom side. What part of the coordinate do I already know? The y. So the y is a half. Now we solve for x. And how can I find x? Now we can just do Pythagorean Theorem because we won't have two variables. Okay. How about, let's see, how about, Michael, can you set up Pythagorean Theorem for me with that triangle?
I don't know.
Can you tell me what Pythagorean Theorem is? Don't worry about the numbers in that triangle, just the formula in general.
I don't remember.
You want to help him out? What's the formula of Pythagorean Theorem? Yep.
A squared plus b squared equals c squared.
Can you tell me what the A, the B, and the C are?
The A is 1/2 and the B is x.
Sorry, can you know what? You don't even have to be specific. Just tell me in general, what are A and B?
Oh, the lengths that aren't the hypotenuse.
The lengths that are not the hypotenuse, and what's C?
Hypotenuse.
C is the hypotenuse. All right. So now, Michael, could you tell me what would get plugged in for the A, the B, and the C?
1/2 squared plus x squared equals 1 squared.
Good. 1/2 squared plus x squared equals 1 squared. Okay, now solve for x. How about Caleb? What's 1/2 squared?
1/4.
1/4. X squared will equal how much? Yep. 3/4. And when we take the square root of each side, what will x equal? We'll leave it as an exact answer. Caleb?
Square root of 3 over 2.
Square root of 3 over 2. and that is the x value. Square root 3 over 2. Okay. So in the 30, 60, 90, you always have one side that is shorter, and then you always have another side that is longer. You have two numbers, root 3 over 2 and 1/2. If you change those to decimals, root 3 over 2 is about 0.866. 1/2 is 0.5. So 1/2 is a smaller number than root 3 over 2. 1/2 is always the shorter side because it's smaller. So in this case, that's the red. The bottom side, the base that I did in a different color, the base that's in blue, that's the long side. And the long side in the 30, 60, 90 is always root 3 over 2. The hypotenuse is always 1, but that doesn't help. Okay, so 30 is the smaller angle. It goes across from the smaller side, which is always a half. 60 is the bigger angle. It goes across from the bigger side. And the bigger side is always root 3 over 2. If you can remember those two numbers when we do the 60, it's going to be almost the same thing. We don't have to really go through all this work again. Yeah.
So would 60 degrees on the U circle just be double each one? So like square root 3 and 1?
So there's your 60. There's one side. Here's the other side. Put the coordinate over here. Look at the triangle that I just drew for the 60 and compare it to the one I drew for the 30. How did the two triangles compare to each other? Nick?
They're flipped, right? Well, you flip the coordinates, so it's like standing up.
Yeah, it's the same exact triangle, except now it's standing up on the short side instead of being on the long side. So all that's going to happen is now the short side is right here. The short side is always your 1/2. And the long side is always root 3 over 2. And now the long side is going up and down. That's my y. So that's why the 30 and the 60 is just a little bit more tricky, because you got to make sure we get those two numbers right. And we're going to practice, but at this point you should be able to have an idea of how to do everything on the unit circle. Okay. If you had an angle over here like this angle would be 150. You should be able to figure out the coordinate for 150 based off of it just being a mirror image of the 30. Same thing if I asked you about 120. Should be able to figure out the coordinate for 120 because it's a mirror image of the triangle of 60. All right. So the three numbers that you have to remember to do unit circle trig are root 2 over 2. That's the coordinate that's used for 45. And the other two numbers you have to remember are root 3 over 2 and 1/2. If you can remember the three coordinates for the 30, the 60, and the 45, everything else is just a mirror image of those three triangles. All right. I'm not going to try to draw everything on the same diagram because it starts to get a little cluttered. Okay. But let's try some examples. All right, so find the 6 trig functions of 45 degrees. All right, what's the first thing that I need to know to be able to do anything on the unit circle? Sophie? I gotta have the coordinate. Now, if it's a 30, a 45, or a 60, and it's not a multiple, hopefully you'll be able to memorize that pretty soon. If not, you'd have to go back through and figure it out every time, like we did the first time. Okay, that takes a long time. So I don't want to go back through any of these proofs like we did the first time. All right. So what's the coordinate for 45 degrees? Yes.
Square root 2 over 2 square root 2.
Square root of 2 over 2, square root of 2 over 2. And that problem should look very familiar. That was one in the homework. The only difference was I gave you the coordinate. I didn't ask you to figure it out because you didn't know how to figure it out for a 45. But now all the answers are exactly the same as the homework. Okay, well, let's just go through them quick. All right. So Madison, what is my sine?
Square root over 2 over square root over 2.
Can you say it again?
Over 2.
Yeah, square root of 2 over 2. Square root of 2 over 2. How about Lindsay, my cosine?
Square root of 2 over 2.
And which one is it, just so we make sure we know which one is which?
X.
It's the x. In this case, if you mix them up, you'd be lucky they're the same. But you shouldn't mix them up. Okay, and my tangent, Nick?
1.
1, because we're dividing two things that are the same. So we get 1. While we're here, let's just do the cotangent, because that's a quick one. Sophie, what's my cotangent? 1, because if we flip 1, we get 1. All right. And Mabel, what do I get as my first step for the cosecant of 45?
It would be 2 over square root 2.
It would be 2 over the square root of 2. But we need to fix it because we have a square root in the bottom. And Tim, what do you get when you fix that?
Square root 2.
Yes, it would just be square root of 2. Is there any question on how to fix that? Just multiplying top and bottom by root 2. How about my secant of 45? Julie?
Square root 2 over 2.
It's not the same as the cosine. So, Michael, can you help her out? What's the secant of 45? Don't think too hard because there's no calculation you have to do. Any work that you need to do for that one has already been done for you. Just look up above.
It is square root of 2 over 2.
So that's what you get before you flip it, but now I want to flip that. So what do you get when you flip that?
Square root of 2.
Square root of 2. It's the same as the sine. Because the sine and the cosine are the same, then the cosecant and the secant are going to be the same. Any questions on that one? Yes?
I feel like it might be beneficial if we go over how to simplify that from, 2 over square root of 2 to...
The square root of 2 over 2?
No. 2 over the square root of 2, just to simplify that.
Oh, well, when you have 2...
2 times that, yeah.
Oh, when you flip it, okay. So when you have 2 over the square root of 2, and you want to fix it, you multiply top and bottom by square root of 2. You get 2 root 2 over the square root of 4, which is 2.
Divide both by
But then the 2's cancel. So it's just square root of 2. Right, let's try this one. Find the 6 trig functions of 30. Now, this is one that the two numbers that are going to be involved are root 3 over 2.5, but we have to get them in the right order. Okay, they're both positive because you're in quadrant 1. But if you're not sure which one comes first, this is what I do in my head. I think of the circle, think of 30, and I imagine that triangle in my head, and I say, okay, where is the long side? Is it on the bottom, or is it going up and down? And I say, no, it would be on the bottom. So what's going to be the coordinate for 30? Abel?
Square root 3 over 2.
Yep. Square root 3 over 2, 1/2. And now we can go through our trig functions. John, what's the sine?
1/2.
Caleb, the cosine?
Square root of 3 over 2.
2. Madison, my tangent.
1/2 over square root 2 over 2.
And when you divide those, what cancels out?
The 2.
The 2's, because when you divide by a fraction, you flip and multiply, and that would cause the 2's to cancel. So you would have this, 1 over the square root of 3. But Sophie, what do you get when you fix that?
Square root
Over 3.
Over 3. Okay. How about Maddie? What's my cosecant?
2.
Sorry, say it again.
2.
2, yeah. That's my cosecant. Lindsay, my secant.
2 over square root 3 before simplifying.
Mm-hmm.
Then it's 2 square root 3 over 3.
Good. 2 square root 3 over 3. Now for the cotangent, you have a choice. You could either flip what I have circled in black, or you could flip what I have circled in red, because there's an equal sign between them. They're the same. Which one would be better to flip? Yeah.
First one.
The first one. How come?
Because you don't have to simplify it.
Yeah, if you flip it, you're done. Okay, if you flip it, you get square root of 3 over 1, final answer. If you flip the one in red, you're going to get 3 over the square root of 3. You're going to have to go back through all the work to simplify it again, and you'll get the same thing. So that's 30. Let's try this one. Find the 6 trig functions of pi over 3. Now they're asking in radians. What's pi over 3 in degrees, Matt?
60.
That is 60. So now I have to think in my head, I'm visualizing what a 60-degree angle would look like. 60 is closer to the top. So what's going to be the coordinate for 60? Sophie?
1/2 square root 3 over 2.
Yeah, that's going to be the 1/2 root 3 over 2. And now let's just go through our values. Annalise, what's my sine?
The square root 3 over 2.
So that's my y. Nick, my cosine?
1/2.
1/2. Mabel, my tangent?
It would be square root 3 over 1. I mean, 2 square root 3 over 2.
2 square root 3 over 2, which would
Square
be
root 3.
just square root 3. Yep. All right. How about Tim? What's my cosecant?
Your cosecant would be 2 over square root 3, which would end up being, so it would be 2 square root 3 over 3.
Good. 2 square root 3 over 3. Michael, how about my secant?
2.
2. Yep, we're just going to take the cosine and flip it. That one's nice, no root. We don't have to worry about fixing anything. And what about my cotangent? And if you're not sure what to flip, think of it like that. John?
Square root 3 over 3.
Square root 3 over 3. Now, because 30 and 60 are the same coordinate with the x and the y flipped, when you compare the answers between the 30 and the 60, you get all the same answers. They just switch places. The sine and the cosine switch places. The cosecant and the secant switch places. And the tangent and the cotangent switched places. Now, every answer that you see is going to be a variation of either one of the answers you see here or one of the answers you see for the 45. The only variation is you could have a negative in front of it. And that's it. And that happens when we start looking at angles in other quadrants. So, this time, they only want us to do 3 trig functions. Okay, we're not going to do the ones where we flip them, because we've practiced a few at this point. Now we want to think 135, is that a multiple of 30 or is that a multiple of 45?
45.
That's a multiple of 45. So what is the number that's always involved in a 45-degree angle coordinate? Yep.
Square root 2 over 2.
It's always a square root of 2 over 2. Now we just want to kind of visualize where 135 is. 90, 180. There's 135. So what's going to be my coordinate for a 135? Mass?
Negative square root 2 over 2.
Mhm.
Square root 2 over 2.
Perfect. And now we're doing the exact same arithmetic we did with 45. The only difference is the x value is negative. So, sine, root 2 over 2. Cosine, negative root 2 over 2. And my tangent. What would that be? Caleb? Negative 1. And if you wanted the other 3, all we have to do is take the 3 that we have and flip them. That's it. Questions on 135? All right. Let's try this time now. We're just doing one trig function, just the sine. This is more how it will be set up on the test. I'll give you an angle. I'll ask you for 2 things. First, I'll ask for the coordinate, and then I'll ask you to do something with the coordinate. In this case, the sine for 7 pi over 6. All right. What might help us to make 7 pi over 6 easier to work with? Yep.
Pi over 6 is 30.
This is 30. Okay.
Times 7 is 210.
Times 7 is 210. So that's the angle that we're working with, 210. Is that a multiple of 30 or a multiple of 45? 30. Whenever you have a multiple of 30, it's not right in the middle of the quadrant. It's closer to one of the axes. Closer to 180 or closer to 270? Closer to 180. So let's put that in about like that. There's my long side. There's my short side. So what's the coordinate for 210? Keeping in mind you've gone left and down. That tells you the kind of number. Just put the 2 numbers in the right order. Yep.
Do negative square root 3 over 2.
Yep. X side is the long and
Negative 1/2.
negative 1/2. Now all they want to know is the sign. So in this case, what's the sign? Yep. Negative 1/2. Huh. Okay, so the 2 things I would ask you for is coordinate and then the answer. Okay. What else? Oh, we have another. All right, let's do cosine since we have it right there. What's the cosine? Yeah.
-2.
Negative what?
-2. Or, no, you're inverting it, so it would just be 2. Am I?
Unless he can't, this is the fun.
Yeah, no flipping here. What is it?
The x.
Yes.
Yeah, that's just negative the square root of 3 over 2. I don't know why I'm...
Yeah, the sine and cosine, those are the easiest 2 because you're given them in the coordinate. You don't have to flip them.
Why am I thinking cosecant?
You don't have to divide them.
I'm tripping out.
Yeah, the cosecant would be negative 2.
Yeah.
Remember, when you flip something, it doesn't change if it's negative or positive. Some people mess that up. When you flip it, you leave the negative alone. Just flip the 2 numbers in the fraction. All right, let's try a different one. Let's do...
This is the naming convention.
Actually, that's pretty good. So does anybody have questions on the angles that we can do in the unit circle? You can do anything that's a multiple of 30 or 45. That gives me 16 different points to ask you about. 3 in each quadrant, and then 1 on each axis. Okay. Now, what if you get an angle that's not a multiple of 30 or 45? Well, it's not something that we can easily find the coordinate for. Technically, if it's a multiple of 15, we could at some point. But for now, if it's not a multiple of 30 or 45, we're going to use the calculator. All right, so let's look at how we do that. Find the 6 trig functions of 42 degrees. Round your answer to 2 decimal places. Okay, what's the unit on the angle this time? It's in degrees. So the very first thing I should do is check my calculator and make sure I'm in degrees. Because your calculator, if you're in radians, it'll give you answers. It'll just give you answers in radians, and that's not what you want. So anytime you press sine, cosine, or tangent, check the mode button first. All right, I'm in degrees, that's perfect.
I'm in radians, how do I get out of that?
How do you check what you're in?
It says it right at the top of the screen.
Oh.
Or yours doesn't, actually. To check what mode you're in, press mode. And then if you're using one of my calculators, you can pick radians or degrees.
Okay, thank you.
I'm already in degrees, so you just highlight it, you hit enter. And let's type them all in. So sine 42. It's a good habit to close the parenthesis, even though it technically doesn't matter in this problem. You should. So sine 42, cosine 42, tangent 42. That's how you do the 3 on the left. Just like that. Now, the 3 on the right. Do and check to make sure you're getting these answers. If you didn't, then something's wrong. Do we have a button on the calculator that says CSC? No. So how have we been finding the cosecant all along? What have we been doing? We have to do the same thing. Caleb?
Find the reciprocal of sine.
Find the reciprocal of the sine. So 1 divided by sine 42. I should have closed the parenthesis, I meant to, but it didn't mess anything up. How would we find the secant? What would I type in? Mabel?
It'd be 1 divided by cosine 42.
Yep, 1 divided by cosine 42. And how would I find the cotangent? Sophie?
1 divided by tangent of 42.
1 divided by tangent of 42. Except you should type in 1 divided by tangent 42. Tangent 42. Okay. And there are your other 3 answers. Just ignore this one. I made a mistake. So 1.49, 1.35, 1.11. 2 decimal places is usually pretty good. Sometimes they'll ask for 3. But there's your 6 trig functions of 42 degrees. Let's take a look.
1 divided by sine is cosecant, correct?
1 divided by sine is cosecant. Yep. This one, they're only asking for the sine and the cosine. Okay. What do they want me to do? Somebody just read this to me. What does that say? Yep.
I want you to find the sine of 10 degrees. Or, sorry, 10 radians.
10 radians. If I type sine of 10, my calculator will give me an answer, but it's not right. Okay, that's degrees. So what we want to do is press mode, highlight radians, hit enter, and if you're using one of my calculators, it will now say radians at the top. Maybe yours does too, depends on the model. Press sine, 10, enter. Cosine, 10, enter. And those are the 2 answers you should get. Negative 0.54 for the sine, and negative 0.84 for the cosine. Okay, any questions on that? Now, let's go back to 42 for a minute. Let's take the sine of 42. Except I want to do it back in degrees. What did we say you can add and subtract to an angle, and it still comes out exactly the same? Yeah, Maddie?
360.
You can add or subtract 360. What do you get if you add 42 and 360? 402. What do you think is going to happen when I hit enter? What am I going to get?
Same after you did it, you got the same.
It's exactly the same answer. I could also do sine of 402 plus 360. Again. And what do you think I would get here? Same answer. I can keep adding 360 as many times as I want, or I could do the sine of 42 and I could subtract 360. Adding and subtracting 360 to the argument when you're doing the sine, the cosine, the secant, or the cosecant will not change the answer. What two trig functions did I just leave out? I said 4 of them it wouldn't change the answer, but there are 2 that it would. Yeah?
Tangent and cotangent.
The tangent and the cotangent. Let's just pick tangent of 42. There you go. Let's add 360 to it. Tangent of 42 plus 360. Okay. So, yes, it comes out the same if you add 360, but what I meant to say is you could also add something else. The reason 360 works is because it's 180 times 2. That's why it works. So with tangent and cotangent, you can actually add 180. If you try that with sine and you add 180, you will not get the same thing you started with. Okay? Depending on, yeah, you'll never get the same thing. If you pick an angle and then do sine of 55 plus 180, came out similar, but it came out negative instead of positive. So can't add 180. So let's just finish up by writing down what we just said. With sine, cosine, secant, and cosecant, you can add 360 degrees. Where is it? Is that, yes, right here. Well, let me write that property first since we just mentioned it. These are special properties of sine and cosine. So the first one says that if you have sine of an angle or cosine of an angle, you can take that angle and you can add 360 degrees or 2 pi, and the n means it's a multiple as many times as you want. You could add 2 pi times 1, 2 pi times 2, 2 pi times 3. You can add 2 pi as many times as you want. It's just bringing you around an extra revolution. Okay, I demonstrated it with 360 because I think the arithmetic is easier to see. That's called the periodic property of sine and cosine. Generally, we try to work with the simplest angle we can, which is the one between 0 and 360. If you already had an angle between 0 and 360 and you add 360 to it, you're just making it harder. So we wouldn't do that. And this works for sine, cosine, secant, cosecant. When we talk about tangent and cotangent, we can actually make this a pi. But don't worry about tangent and cotangent. And the other special property for sine and cosine is that you can plug in anything you want into them. Positives, negatives, fractions, decimals, 0. But the answer that you get will always be between these two numbers. And I don't know if you noticed that when we did like sine of 42. We got decimals for an answer, but it was always between -1 and 1. For sine and cosine. All the other ones, we'll talk about those later on. I don't want to get into showing you the graph on the calculator right now, but basically, that's what the graph of sine and cosine both look like. They're always between 1 and -1. Any question on that? All right. So, let me just double check and see if there's anything else there we can cover. All right, so 13 to 17, that is actually just finding sine and cosine. You don't even have to do all 6. 21 to 25, that's doing 4, so you're still not doing all 6. 29 to 32, those are all on the calculator. 37 to 40, you're going to need a calculator for those. 45 to 47, finding 2 trig functions. I don't think there's any way you have to do all 6. 50, don't have to do. And the rest should be okay. Okay, so we'll take a look at those tomorrow. And then we'll start the test and we'll finish it on Wednesday. If you're looking for test topics, remember those are in the last video.